This video will entail a theoretical discussion of peak instantaneous amp flow in an inductor as a function of constant voltage DC pulse duration. By way of background, there are two named laws of nature that we are concerning ourselves with here. The first is Faraday's law of induction, which states that the magnitude of the EMF established, electromotive force established, is directly proportional to the rate of change of magnetic B field strength. So this total change in the field is termed magnetic flux. So it's magnetic flux per unit time that determines the establishment of the EMF, and the EMF is what determines the magnitude of the inductive spike and the current that flows therein. The second law to be considered is, well, it really goes back to Faraday, that for every current that's induced, if there's another conductor in the vicinity, a photonegative current will be established. This is referred to as Lenz's law, and the current established in adjacent conductors is one such that it opposes the flow of current through the conductor. This induced dynamic resistance will be greatest when the rate of magnetic flux change per unit time is greatest, and will no longer be present when the inductor is fully saturated and at its maximal field strength for the given voltage applied to it, as at that point there is no longer any further change in the magnetic field and hence no further induced magnetic field. Now it's a bit of a change just to talk about theory, and one must be careful, as has been shown in previous videos, that when one looks at the experimental results, one may find things that conflict with what is canonically held to be true as laws of nature. This has been demonstrated in previous videos, and there aren't good explanations for what's seen there. However, usually when you get to things where you can easily trace it back to a person, and likewise when it is used in practical application, the science, quotation marks, often seems to be less fraudulent. Therefore, we will use as a springboard this electronics tutorial site, which I believe is maintained by Texas Instruments. And I haven't gone through all of this, but it is, in my view, just top-notch. And so if you want to get up to speed on some of this, these are the things to go through. So we can go to the page on inductors, and there are within there a few brief chapters, and we're going to go to LR series circuit. Aside from the fact that experimental values sometimes disagree with what's canonically held by consensus to be valid, there is also, of course, the issue that I don't have a formal education or work experience in this area, and so of course I can be misinterpreting what others who've spent a career in this are actually saying. So one needs to be careful and humble as well, and so that's also a warning to others that I may step in a gopher hole, or I may be entirely off base. So think it through yourself and do the work yourself as well. The third reason to be careful, is that, and we will, when we set up a little Arduino circuit, demonstrate what I'm getting at here, but that while the equation may be valid within certain parameters, oftentimes there are other variables not being discussed that are more important. So, for instance, we're going to be talking about an LR series circuit. However, what we're interested in is discharging a capacitor into an inductor, giving one an LC circuit. There'll, of course, be some resistance present as well. So I guess you would call it an LRC tank circuit. And what determines resistance there is not only the dynamic resistance of the inductor, but it is also a function of the cycles per second, and specifically whether one is in or out of resonance or in or out of a harmonic therein. I believe it was Tesla in one of his patents said, for any system like that, there's a specific frequency where it behaves as though the only resistance present is the straight line DC resistance, as though there is no dynamic resistance whatsoever. And so we're going to examine that experimentally in a subsequent video, but it's, I think, fun and worthwhile to have this discussion, which shall begin shortly. So once again, to summarize, there is a dynamic resistance or a reactance to an inductor, wherein when you put in current, a magnetic field becomes established, and there is a magnetic flux associated with that field being established. That magnetic field, especially in a coil of wire where the current wavefront is passing through a wire with numerous adjacent wires around it, creates an induced magnetic field which opposes the flow of current. While it's a magnetic resistance, it is resistance, similar to the resistance that you have, I would say identical to the resistance that you have just bumping into stuff as you move through a circuit. The strength of the resistance can be orders of magnitude at times greater than the established DC resistance that's present once the inductor is fully saturated. And again, the resistance varies as a function of magnetic flux per unit time, and so it's not a constant resistance. If it were not present and there was only the straight line DC resistance and no inductance, now of course there'll never be a situation of no inductance that I can think of, but in idealized terms, if there were no inductance, as soon as that switch is flipped, then the current established, and established, I would guess at the speed of light, is equivalent to Ohm's law, V equals IR, and the amp flow will be constant, and so it would be a perfect square. Because of the dynamic resistance, it's not a perfect. So if we go back to our LR series circuit, the first thing they're talking about, well, maybe not the first thing. Well, okay, here it is. It was in an earlier chapter that they were talking about what I was going to get to. So this is the expression for what the amp flow is at any time for a given inductor as a function of the voltage, the straight line DC resistance, the inductance, and the time. So here you have a specific time. Here you get an amp flow out where V is in volts, R is in ohms, that's the straight line DC resistance, L is in henries, the inductance of the coil, T is in seconds, E is the natural log. Yeah, so here they're talking about the time constant, which is that this is going to give a curve, and after 5 time constants, the coil is essentially saturated at 99.9 something % saturated, and there's no further change in magnetic flux. After one time constant, which is referred to as the tau time of a coil, the coil is 63% saturated or 62% saturated. And the actual number of seconds or fraction thereof to become fully saturated will vary for any given inductor as a function of the resistance and the inductance of the coil. The volts won't change the tau time of the coil. They will only change what your amp flow is. So L divided by R gives you the tau time. Your inductance divided by your resistance gives you the tau time of your coil. So they just state this explicitly here. The time constant is given as L divided by R, and in which V over R represents what your final state steady current value will be after 5 time constants. And then here they kindly graph it for us. So here is the y-axis, which is amps, and the x-axis, which is time, expressed in units of the time constant. So after 5 time constants, you're at a steady state value. And here is the graph of amp flow. Amp flow moving up like that with this curve to the steady state. And similarly, voltage between your input and the inductor decreasing until finally current is flowing at the maximum rate for the given voltage. Recall once more that the establishment of the EMF is something that occurs only with magnetic flux. And so once the steady state is established, there's no more magnetic flux as there was here. When the coil is shut off, then again there's a curve as it returns to its previous state. So if you were looking to grab the inductive spike, if you charged a coil up, there would be one inductive spike you could grab there. It would be difficult to do because without a short, to grab this charging up is what's done in what's called a boost circuit, a boost DC-DC converter. And then the coil will collapse when you shut the power off. If you grab that inductive spike, that's a setup with a diode termed a buck boost DC-DC converter. And so you can see if you turn the power on and left the coil going for a day, you would get one spike, and it would have a specific, speaking of the buck boost, or either, you would get, let's just speak of the buck boost, you would get one spike per day. If you did it for 1 hour, then you would get 24 spikes per day, and you'd still essentially be putting in the same number of watts. So you can see the first thing is you don't want to go and leave the coil saturated. Now, one can say that if you went to 5 time constants and then shut the thing off, that would be the maximal EMF that would be established. And you could grab that, and for a given voltage and a given coil, you're not going to get a bigger EMF than having fully saturated the coil. However, if we recall what we were talking about a little bit earlier, let's say you went to 4 time constants. Well, now, instead of 99.9, maybe you're at 99.8. So you get 99.8% of your inductive spike, but I mean, first off, you would say you're only using 80% of the power, but it's actually even less than that, because here you can see your amp draw is nearly maximal, while all in here it was less than maximal. So you're using less than 80% power, probably, I'm guessing 65%, 70% of your watts to establish a magnetic field strength that's only 99.8 instead of 99.9% of the maximal field strength of the inductor. Now we go here, you can kind of see the same thing. And here's why I had the previous discussion, is remember the different slopes of the line. The more vertical the line is, the better off you're doing. So we can go from here to here, and now you're getting rid of all of this, which is nearly saturated, and you're only going for 3 seconds, and you're getting perhaps 98% instead of 99.9% of your maximal field strength. And similarly, we can move to the tau time. Now here you're only putting in power for 1/5 as long, and all through here you were close to the maximal amp draw, while here it was far less, and you've achieved 63% of your maximal amp flow, so therefore 63% of your maximal B field magnetic strength, and you've used far less than 1/5. It's like 1/10 or less than that of watts in order to establish that. And then the question is, does that continue? So there are 2 ways to answer that question. And the first way would probably be the best way, which would be you want to integrate for the area under the curve for a given time. And when you do that, you can say precisely for a given time how many watts you used. Because of course, I'm saying you need calculus because this is a curve. Now, I will leave it as an exercise to the viewer to integrate this curve. That's a little bit of humor. I don't know how to do that. It's been a long time since I've done calculus, and I could try to go back to look at it. However, this is not the most simple formula. So you would need to integrate that. You need to get, what is it, the antiderivative. And once you have that, you can calculate. But normally, you know, it's like y equals x squared, that kind of thing. Okay, it's easy. This is I equals v over r, t minus natural log to the negative rt over l. Someone who's good, go ahead and do that. But we can use a spreadsheet and do essentially the same thing, and sort of a application of the same idea, but just do a spreadsheet. So in other words, we'll calculate instantaneous amp flow, have the time, calculate instantaneous amp flow, have the time, calculate instantaneous amp flow, cut the time in half again, and then we can look at the amp flow at each of those times, and we can approximate what you could determine precisely with integrating this curve. So before going to a spreadsheet, we'll look at some of the example problems that they kindly provide. So they give a coil with 40 millihenries and a resistance of 2 ohms, and it's connected to an LR series with a 20 volt DC supply. So what's the final steady state current? V over R, 10 amps. What's the time constant? L over R, 20 milliseconds. What's the transit time then? 100 milliseconds. What's the induced EMF? This is what we're interested in. What's the instantaneous current at 20 milliseconds? And so that's given here. So what we'll do, since they provide this, is we'll use a coil initially with the exact same parameters and plug in the same values here and make sure that we get the same result for instantaneous current, 6.32 amps at whatever the time value I think they said 20 milliseconds. Then once we have that, as well, first we can make the coil anything we want, and then, as I said, establish the instantaneous current over a number of points along that curve, and just have fun looking at it. Again, we have seen from the curve that obviously, you don't want to go past the tau time in terms of pulse duration for any sort of efficiency. But what I'm curious about is if we accept the validity of the equations, then what happens here? And so we'll just keep, go by half, go by half, go by half again. So let me set that up in a spreadsheet. So here we have, like the example that was shown, we have the equation there for instantaneous amp flow. Coil, we have the volts at 20, a coil with resistance of 2 ohms, inductance of 40 millihenries, and there is E. And so we say time there, and then V over R, and that's what your end state amp flow is, and that's 10, so that's just like they said. And then you got this part, and that equals that, and so your instantaneous amp flow will be 10 times this, 6.3212 at 0.02 seconds. Going back here, 0.02 seconds, 6.32 amps. So we got it. Now let's have some fun. First, we can slow this coil down a bit by either increasing the inductance or decreasing the resistance. So let's make the inductance 10 times larger, 0.4. And so that's where that is. We see the amp flow is much less now. So now the tau time of the coil is 0.2 seconds. And I just picked that because that means that your transit time to saturation is 1 second. And so if we put in 1 second, you're at 9.93. Eventually you get to 10. Now, let's make subsequent times equal to this divided by 2. So we're kind of fudging calculus. Let's go even further. All right, that's enough for the moment. This will be tough. Ta-da! All right, now we're in good shape. So are we having fun yet? So now, this then is the strength of the magnetic field that's established, because the magnetic, the coil is going to be the same with all of these, so the magnetic field strength will be determined by the amps that are flowing through. So I don't know if this coil has 10 turns or 10,000 turns, but the amps will determine the the amp turns. And of course, you know, if it has more turns, it might behave differently. So, you know, but I'm just saying that we don't know how many turns a coil that was wound that gave these specifications would have. But whatever it is, this is what's going to determine the magnetic field strength. And then the magnetic field strength will determine, you know, how much magnetic flux you can get. And then, you know, however quickly it occurs. So the next part we want to look at is how many watts did we expend to achieve this particular amp flow. Well, first I guess we should review what is a watt. So, you know, a watt is unit of work, 1 joule per second, and it's also 1 volt times 1 amp. So watts are volts times amps, and that's your unit of work. So we can put in a column for watts, and so here's your amps, your voltage is 20, so that's what it was there. Here's, you're using 198 watts when you have this, and that 198 watts will just continue pouring out at that rate, actually going up to 200, you know, while you keep throwing power at the coil, because at this point the coil is saturated. Here, at half of the transit time, you were at 183 watts. Here you were at 142. Here, which is a little bit more than the tau time of the coil, you were at 92. Recall I'm sorry, the tau time of the coil is 0.2, so 142, you know, there it is, 126. So that's all good, and then down to there. But what we want to know, and this is not straightforward without calculus, is you're at 198 watts here, you know, at half that time, 100. So how many, what's the average watts here? You want to know watt seconds. So in other words, how many watt seconds how much energy did you use in order to establish this? Put another way, we want to know how many coulombs of charge were expended in order to establish this magnetic field strength, so on and so forth. Okay, let's forget about watts. What we're interested in is how many coulombs of charge exited your battery or capacitor or whatever in order to establish a given amp flow, which is directly proportional to a given magnetic field strength. And again, if anyone's good with calculus, please integrate that curve, and this is like repeating that and showing why calculus is useful at the same time. So we don't know exactly, but we can approximate. This is, I guess they would call like a rectangle approximation. So we'll say that the average amp flow between 1 second and a half second was this plus this divided by 2, so 9.58. Between 0.5 and 0.25, it was this, and so on and so forth. So for 0.5 seconds, you had that amp flow, and for 0.25, you had that amp flow. 0.125, you had that amp flow. I hope that's making sense. That again, coulombs is going to be how many electrons exit your battery, and 1 amp is defined as a coulomb per second. Do I have that right, or where is it? I looked it up. 1 amp electric charge delivered by 1 ampere in 1 second, and it's that many electrons. So that's telling you how many electrons you're using. Where am I? So again, as an approximation, we can say that for this half second, The amp flow was about that. Might have been a little higher because it's a curve, but we were approximating. And then from 0.5 to 0.25, it was about that. So that times half a second gives you 4.77. Now again, because coulombs are equivalent to amps per second, if you had 9.55 amps per half a second, you have that many coulombs. So this column is what we want. This is the coulombs that are leaving your battery, the rate. It's the coulombs leaving your battery at each of these intervals. Now, the last part is for this one, it's going to be the summation of all of these. For this one, it's going to be the summation of all of them but the top one. So again, as a good approximation, your total coulombs will be equal for this one to this plus this plus this plus this plus this, right down to the end there. And for the next one, down to the end there, down to the end there, and so on and so forth. We don't have this one because we don't know what the next thing would be to average it. But we have these. So now we know how many electrons left, and we know what the strength of the magnetic field was that was established per the peak amp flow. So let's put those in a ratio. So equals this divided by this. 0.797. And everything lines up, so let's just scroll it down. Okay, now we've got something. So I'll go back and double check everything before I post this. But as long as I did everything right, that's, you know, you can say down to the electron. That's how many electrons exited your power source in order to establish that peak instantaneous amp flow. And so that number of how many electrons divided by that gives you this. And then the next one gives you that. So it's about twice, a little more than twice as good. Right down there. I'm just going to do 1 over this so that we can compare it more easily. And so if I didn't do anything stupid, and, you know, of course, there's always real world stuff and so on and so forth. But we can say that a pulse of this duration is, you know, more than 2,000, what is it, maybe 2,200 times more efficient for how many electrons you spent in order to establish a particular field strength. So if you're looking to gather the inductive spike, this is more than 2,000 times more efficient than just charging the coil to 5 tau times. Now, of course, this will give you the strongest inductive spike. This inductive spike here, let's see, 0.02 versus 9.93. So it's on the order of 500 times weaker. However, for the number of coulombs of charge you expended to get this magnetic field strength, it's more than 2,000 times more efficient than here. So I'm just going to, on my own, you know, offline here, I'm going to go through everything I did here again and make sure I didn't do anything goofy, because this is the first time I've really formally looked at this. But when people say, oh, you want short pulses, well, now you know why. Now again, when you get into the real world, it can be much different. And one of the things is that with an LC circuit, the resonance is also affecting the spike. Furthermore, if you have a very brief pulse, I mean, will your diode even be able to catch it? Will it be able to rectify it? Further, if it's very weak, then perhaps you run into other issues with components. So one thing you might think to do is, if you have a very low resistance, high inductance coil, that's going to make your tau time, instead of 0.2, maybe it's like 2 seconds. Now, one issue there is if you want a low resistance coil, you're going to have big fat wire, and then you run into skin effect as you go faster. So that's another issue, is in the real world, is that as you go faster here, you're going to run into skin effect. And the skin effect will decrease the effective diameter of the wire and thus increase resistance. And so that's yet another parameter to get into. And one of the ways to get around that is Litz wire. And not to mention him every video, but you notice John Bedini always used Litz wire. Not always, but in many of his machines, you would see him using Litz wire. And so that allows you to go quicker without running into increasing resistance, not from Lenz's law, but from skin effect. But all that said, that's why you want to use short pulses. We don't need to talk about the Dirac C. We don't need to talk about the luminiferous ether. All you got to do, this time I'm not arguing against any conventional stuff. This is stuff they use, Hewlett-Packard. They gave me this equation. I just plugged it in and ran the numbers, and that's what you get. But to make that work with a DC-DC converter, where you start to get out to here, you run into other issues. You run into the resonance, you run into skin effect, you run into what can your components do when they're going fast. So, again, the bottleneck very often might not be the coil when you're going this fast. The bottleneck might be, your transistor, whatever your switch is. So that's something to keep in mind. So again, I just never plugged this in. This is the first time I plugged all of this all the way through. I'd kind of looked at it, a little bit, with a calculator and a little bit of this, but I never just went ahead and looked at this. And so this is what you see, and this is why one might say for an efficient DC converter, it's better to use brief pulses of DC current.